Welcome! In this video, we present the update step in the MBM tracking filter. In the MBM update, we start with the parameters of the prior MBM density, and the goal is to compute the base posterior MBM density for the standard multi-object measurement model that has a probability of detection, PD, a measurement model G, and Poisson cluster with intensity lambda c. And specifically, we're looking for the parameters of the posterior density, and that is what we will learn about in this video. When we have the standard point object measurement model, the MBM update can be summarized by 3 points. For each prior multi-Bernoulli in the mixture, we will have multiple data associations. This is similar to the posterior mixture density that we had in N-object tracking. Each prior multi-Bernoulli and each data association will result in a multi-Bernoulli in the posterior multi-Bernoulli mixture. And for each pair of prior multi-Bernoulli and data association, for each Bernoulli we will have 2 possibilities. Either the Bernoulli is associated to one of the measurements, or it is not, in which case it's misdetected. So we can say that the multi-Bernoulli mixture update has 3 building blocks. First, there is the update of a Bernoulli to which we have associated a measurement. Then there's the update of a Bernoulli that was not associated to any measurement. And lastly, we have the posterior log weight of the posterior multi-Bernoulli that results from updating the prior multi-Bernoulli with a data association. And similarly to MHT, an implementation of a multi-Bernoulli mixture filter can be either so-called hypothesis-oriented or so-called track-oriented. And in this video, we will briefly explain a hypothesis-oriented MBM update. Later in the course, we will further discuss the computationally more efficient track-oriented MBM. An hypothesis-oriented MBM update can be explained as follows. The input to the update are the parameters of the prior MBM density, so that is the log weights and the Bernoulli parameters. And we can start by initializing a posterior hypothesis index H with a subindex K. For each prior multi-Bernoulli, indexed by H with a subindex k-1, we start by creating a cost matrix L, and we compute some number m of associations, theta m, using an optimal assignment solver. The number of associations m to compute here can be determined just like we did in multi-hypothesis tracking for a known number of objects. For each association m, we first increase the posterior hypothesis index, and then we compute the posterior parameters. This includes computing the parameters of detected Bernoullis, misdetected Bernoullis, and the posterior log weight. Later in this movie, we will explain these 3 steps. After computing the posterior multi-Bernoulli parameters for each prior multi-Bernoulli and each data association, the number of posterior multi-Bernoullis, capital calligraphic H, is equal to H subindex K. The log weights that we computed for each posterior multi-Bernoulli have to be normalized, and this can be done in the same way as was presented earlier in the course. And once the posterior log weights have been normalized, we have the parameters of the posterior multi-Bernoulli mixture density. Let's begin with the Bernoulli update when we have an associated measurement. For a prior hypothesis H, if the association for the ith Bernoulli, theta I, is equal to J, then Bernoulli I was associated to measurement J in this data association. And the updated parameters for the ith Bernoulli are that the probability of existence is equal to 1, and the updated state density is given by the base update. So we have the probability of detection, PD, multiplied with measurement model G and the prior, and then this is normalized by dividing by the integral. The posterior probability of existence conditioned on this association must be equal to 1, because we cannot associate to an object that does not exist at time k. So it's important to remember here that the probability of existence is equal to 1 given this data association. We then also have the log weight for the posterior multi-Bernoulli. So the fact that this probability of existence is 1 does not mean that we are certain that there is an object there. It's only within this particular hypothesis. Lastly, the predicted log likelihood which we will need to compute the log weight of the posterior multi-Bernoulli, is defined as the logarithm of the probability of existence multiplied by the integral of the probability of detection, PD, the measurement model G, and the prior density. If we compare to tracking n objects, the difference is that now we have the probability of existence in the log likelihood. Let's take an example with a constant probability of detection and a linear and Gaussian measurement model G. Assuming that we have Gaussian Bernoulli state densities, the prior parameters are the probability of existence R, the Gaussian mean mu, and the Gaussian covariance P. The posterior probability of existence is 1, like we just saw, and the posterior mean and covariance are given by the Kalman filter update. The predicted log likelihood is the logarithm of the prior probability of existence multiplied with the probability of detection, and a Gaussian PDF evaluated at the measurement with mean given by the predicted measurement and covariance given by the innovation covariance S. That was the Bernoulli update when a measurement is associated. Next, we have the Bernoulli update when a measurement is not associated. So in other words, when there's a misdetection. For a prior hypothesis H, if the data association for the ith Bernoulli, theta I, is equal to 0, then the updated parameters for the ith Bernoulli are that the posterior probability of existence is equal to the prior probability of existence multiplied with the probability of misdetection, PMD, divided by 1 minus the prior probability of existence plus the multiplication of the prior probability and the misdetection probability. The misdetection probability, PMD, is defined as the integral of 1 minus the probability of detection and the prior Bernoulli state density. If the probability of detection, PD, is constant, this integral has a trivial solution. And if PD is not constant, and the integral does not have an analytical solution, then the integral can be solved approximately, for example using sigma point integration. The posterior Bernoulli state density is equal to 1 minus the probability of detection multiplied with the prior state density and divided by PMD. And the division with PMD, it normalizes the density. The posterior probability of existence, conditioned on the association theta, can be understood as being the relative probability of two possible explanations for why there is no object measurement for this particular Bernoulli. First, we have that an object does exist, but was misdetected. The probability of this is the product of the probability of existence and the probability of misdetection. And then we have that the object does not exist. And if the object did not exist, then of course it would not cause any detection. And the probability of this is of course 1 minus the probability of existence. When a measurement is not associated, the predicted log likelihood is the logarithm of 1 minus the prior probability of existence plus the probability of existence multiplied by the probability of misdetection. Let's take an example again with constant PD and a linear and Gaussian measurement model G. Assuming Gaussian Bernoulli state densities, the parameters are R, mu, and P. The posterior mean and covariance are trivial in this case. Because PD is constant, the posterior mean and covariance are equal to the prior mean and covariance. The probability of existence is given by the expression shown here. Because PD is constant, the integral to compute the probability of misdetection is trivial and is equal to 1 minus PD. And lastly, the log likelihood for this example is given by the expression shown here. We can illustrate what the posterior probability of existence is for some different values for the prior probability of existence and the probability of detection. Here we've plotted the posterior probability of existence as a function of the prior probability for 5 different values for the probability of detection, ranging from very low, 0.05, to high, 0.95. We can see that for any given value of the prior probability of existence, the higher the probability of detection is, the lower the posterior probability of existence is. This is natural. The higher PD is, the lower the probability of misdetection is. And the lower the probability of misdetection is, the more probable it is that an object does not exist, relative to how probable it is that the object exists but was not detected. For the posterior multi-Bernoulli mixture parameters, we also need the posterior log weights. These can be obtained by computing non-normalized log weights and then normalizing, using the normalization that was presented when we talked about n-object tracking. For a prior multi-Bernoulli H and a data association theta, the non-normalized posterior log weight, L tilde, is the sum of the prior log weight, the sum of predicted log likelihoods for Bernoullis that were not associated to any measurements, in other words, misdetections, the sum of predicted log likelihoods for the Bernoullis that were associated to measurements, and lastly, the sum of the log of the clutter intensities for the measurements that were not associated to any Bernoulli. Similarly to how we rewrote the measurement likelihood in n-object tracking by multiplying with 1, we can rewrite the non-normalized log weight by adding 0. So note that the last summation is now over all measurements, which means that this sum is equal for all data associations. So therefore, we can express the non-normalized log weight as the sum of the prior log weight and the sum of predicted log likelihoods for each Bernoulli plus some constant that is independent of both the prior and the data association as shown here. So as mentioned before, these log weights are then normalized using the logarithmic identity that was shown in one of the earlier videos. A good exercise is to compare this expression to the non-normalized posterior weights that we derived in n-object tracking. One of the key differences is that now we do not know the number of objects, and therefore we have probabilities of existence. Now that we have explained the different parts of the MBM update, we can show an example MBM update. We have a two-dimensional scenario with a prior multi-Bernoulli mixture that has two multi-Bernoullis that each have two Bernoullis, and the Bernoulli state densities are Gaussian. The probability of detection is 0.75. The measurement model G is a Gaussian PDF with mean equal to the object state and covariance equal to 9 times an identity matrix. And the clutter is 4 times 10 to the power of minus 4 in the surveillance area and 0 outside. The two-dimensional surveillance area is minus 25 to 25 in both dimensions. So we have a single measurement in this example, which means that for each prior multi-Bernoulli, we have 3 possible data associations. And this gives us a posterior multi-Bernoulli mixture with 6 multi-Bernoullis. Here we can see the 2 prior multi-Bernoullis. The first one has weight 0.3 and the other one has weight 0.7. In both cases, the Bernoullis are visualized by their means and their covariances, and the probabilities of existence are written next to the means, and the measurement is shown as a red square. On the right, we have the 6 posterior multi-Bernoullis. In the top row, we have the ones that result from different data associations for the prior shown on top, and vice versa in the bottom row. From left to right, we have association of the measurement to clutter, association to the Bernoulli drawn in blue, and association to the Bernoulli drawn in orange. When the measurement has been associated to a Bernoulli, the prior Bernoulli covariance is illustrated by a dashed ellipse, and the posterior is illustrated by a solid ellipse. We can see that in this example, the posterior multi-Bernoulli with highest weight is the one that results from the second prior multi-Bernoulli and association to the Bernoulli drawn in blue. If the Bernoulli has been associated to the measurement, the posterior probability of existence is 1, and otherwise it has decreased. So this small example illustrates the basic function of the multi-Bernoulli mixture update. For each prior multi-Bernoulli, we have multiple data associations, and for each one, we get a posterior multi-Bernoulli. And the posterior weights are proportional to the prior weights and the likelihoods of the associations. As we saw when we presented pseudocode for the hypothesis-oriented MBM update, for each prior multi-Bernoulli, we have to compute a number of data associations. And this is handled analogously to how we handle data association in n-object tracking. We use gating to remove very unlikely associations and to group the Bernoullis and the measurements. We form a cost matrix with negative log likelihoods, and then we use some method to find M associations. For example, we can use Murty's algorithm or Gibbs sampling. And all other associations are truncated. So if you feel uncertain about any of these steps, you can go back and review that material after finishing this video. The cost matrix used to compute different data associations can have the following structure, which you should recognize from tracking n objects. We have a left submatrix for the associations between Bernoullis and measurements, and a right submatrix for misdetections. The log likelihoods are defined as shown here. An important difference is that now we have the probabilities of existence, which have to be included in the log likelihoods used in the cost matrix. That was the multi-Bernoulli mixture update. We will come back to the MBM update later, when we talk about track-oriented implementation. Next, we will discuss reduction of the posterior MBM density. Primarily, we will use pruning and capping, and we will also discuss object estimation in the MBM filter.